So I thought I would take this time, especially for those of you who aren't in class this week or may just need a refresher. We're going to embark on a little exploration of a concept called stoichiometry. Now, stoichiometry is probably the trickiest part of chemistry, but it's sort of the most authentic in that we actually get to take a reaction represented by a balanced equation and break it down into information we can actually use. So, this is all going to be based on the concept of the mole. As you know, the mole is the unit we use to measure the amount of a chemical substance. It's equal to a certain large number of particles, 6.02 times 10 to the 23rd. But we're going to simplify this a little bit and just break down the mole into a unit that is useful to us in chemistry. So, I've come up with a little example here, and I want to kind of backtrack a little bit to talking about balanced equations. So, let's say we have a chunk of aluminum foil, and we want to burn it in oxygen. And we can actually predict what's going to come out of that based on what we know about chemistry. And so, the reaction that would result here is right here in the middle of the page. We have the balanced equation right here. This would be a representation of what that might look like. It's actually relatively hard to burn aluminum. It's not all that reactive. But if we were able to burn aluminum in a controlled environment, we would produce this compound called aluminum oxide. And this equation will tell us all we need to know about this reaction and the amounts of substances involved. So, the first thing we're going to do is we're going to think small. We're going to think about this in terms of atoms and molecules. You know that an atom is the smallest particle that represents a substance, and a molecule is made up of more than one atom. We could have diatomic molecules like this one right here. Oxygen is in the form of a molecule because it doesn't exist as single atoms in nature, and so this is a molecule just like this substance over here. Now, technically speaking, we don't refer to ionic compounds as forming molecules, but I think it's useful here to talk about it in that way. So, if we look at this reaction in front of us on a small scale, it's actually pretty simple. We have 4 atoms of aluminum, and we combine that with 3 molecules of oxygen, O2, the kind of oxygen that we have in the air around us, and in that process, if we combine those two, we produce 2 molecules of aluminum oxide. Now, this is great, but we don't ever actually do reactions on this small a scale. We don't really think about reactions in terms of individual atoms and molecules. Luckily for us, though, we can actually use this equation and make a direct relationship between molecules and moles. So that's what we're going to do next. So, we could put this differently, and we can say, because a mole of any substance is the same amount of particles, we can say that 4 moles of aluminum, that is 4 times that very large number of atoms, reacts with 3 moles of oxygen to produce 2 moles of aluminum oxide. Now, we may not have that exact number of moles all the time. In fact, we almost never do. But the coefficients in this balanced equation allow us to establish mole ratios between these substances. Now, a mole ratio is nothing but a fraction. And this fraction relates these 2 substances. For example, we could say that for every 4 moles of aluminum, we would require 3 moles of oxygen. Whether we have a very large amount or a very small amount of aluminum, the ratio between aluminum and oxygen will always be 4 to 3, as long as we're talking about this in terms of moles. Similarly, we'll always have a 4 to 2 ratio between the moles of aluminum and the moles of aluminum oxide, our product, and we'll always have a 3 to 2 ratio between oxygen and aluminum oxide. And we can always use these ratios to relate the amount of one substance to another. Stoichiometry is all about establishing these relationships between substances in a balanced equation. And one thing you're always going to do in in that process is to use a mole ratio to relate one substance to another. So let's look at an example. I came up with a quick little problem based on this equation. And the problem here is how many moles of aluminum oxide can be produced when 17.4 moles of oxygen reacts with unlimited aluminum. And to set up our problem, we want to figure out first what we know, and usually there's a number given to us in the problem. In this case, the number that we're given is 17.4 moles of oxygen. We know we have that much, and we know we have unlimited aluminum. Usually, in these types of problems, one reactant on the left side of the equation will be found in excess, and so we can assume that aluminum is in excess here. We have enough. We have more than enough. We're going to have a bunch left over. So the amount of aluminum doesn't really matter if we know we have enough. And what we want to know is the number of moles of aluminum oxide. And the formula for aluminum oxide, as hopefully you know by now, is Al2O3. So we are going to pick a mole ratio that includes two things: the moles of the thing that we want on the top and the moles of the thing that we know that we're given on the bottom. This will allow us to cancel out the number of moles of the thing that we know, and it will leave us with the units of moles of the thing that we want, our final answer, basically. And so in this case, on top, we're going to have 2 moles of aluminum oxide, and on the bottom, we're going to have 3 moles of oxygen. This will allow us to cancel out moles of oxygen, and it will leave us with aluminum oxide on top. So here's what this looks like. We're going to set up a really simple one-step dimensional analysis problem. We're going to have the thing we start with, the unit that we're given, on the top left corner. We have 17.4 moles of oxygen. This is something we've done 1,000 times already this year. And now we've got to cancel out the moles of oxygen. On the bottom, we put the moles of oxygen, and the number that we use is the coefficient of 3 from the balanced equation. And on top, we're going to use that equation again and write in the coefficient from the balanced equation for aluminum oxide, which is 2. And again, no matter how much oxygen we started with, the ratio is always going to be 2 to 3. And so if we do this math, again, multiplying across the top, dividing across the bottom, 17.4 times 2 divided by 3 gives us an answer of 11.6 moles of aluminum oxide. And this answer makes sense because we have a 2 to 3 ratio, so we would expect that we would have less aluminum oxide. So, now, this is something that we're actually going to do in class, but I'll work it out here for you guys. And the question asks, how many moles of aluminum would we need to react completely with 5.43 moles of sulfuric acid? And so we're going to start here. We have our balanced equation up at the top of the page, and we're asked about aluminum. So we know that on top here, we're going to want to have the moles of aluminum. And I'm going to back this up so we can put a number in front of this. So we're going to put a number there based on what we see in the balanced equation. And on the bottom, we're going to want to cancel out the 5.43 moles of sulfuric acid that we start with. And sulfuric acid, as I wrote here, is H2SO4. So we're dealing here with the 2 reactants in this problem. The other stuff, essentially, we can ignore. We don't really care unless we are asked about aluminum sulfate, or hydrogen gas. So if we were asked a question about that, we would just use those numbers in the mole ratio. So again, the mole ratio is moles of sulfuric acid on the bottom. That's the thing that we're given, the thing that we know, and the moles of aluminum on top. So if we look at the equation, in the balanced equation we have 2 moles of aluminum, and in the balanced equation we have 3 moles of sulfuric acid. So it turns out, and I didn't plan it this way, but turns out that we have the same ratio as before. The ratio is not always 2 to 3. It depends on what we're working with. But we multiply 5.43 times 2 and divide by 3, and we end up with a value of 3.62 moles of aluminum. And again, that makes sense because we would have fewer moles of aluminum than we would have moles of sulfuric acid, because that ratio is always 2 to 3. So I hope that's helpful. Went a little bit long, but I think it's worth it. So I hope this is helpful, and have a great day.